It is pizza.
Exactly.
Don't say, what did you do to bribe them?
She said that.
Everybody here is part of the Bioinformatics.
Yeah, actually, I brought some friends.
Well, I did notice the Kretzler lab around. I did notice a little
Somewhere else.
That
The
would do it.
record shows.
That one.
It'll cut the viewing angle
What?
down. That one.
Well, in the Army, some of the rugged laptop, because of security issues, when you open it up, it actually has like a shoulder go around or something. So somebody can see if they're looking over you, see to the left and right.
I will not hurt my feelings if we start.
Looking over your shoulder like that.
Okay. I will not.
Really, it ought to be accordion, so you just pull it over your head.
Shake hands.
Block out all the light.
I can get hurt in a minute. It just wraps around there. I put my arms through the hole and I put my head in it. Perfect.
I don't know that I can not do that, actually. How's my hair look? I'm going to tell you something. Yeah. No, that's there.
That's the look.
Better.
Welcome everyone. We're gonna go ahead and get started since we have a pretty packed house. This is awesome. Thanks everyone for coming. This is the last talk of the semester. We'll start up again in the fall. I am scheduling people for the fall, so if anyone's interested in presenting, of course, let me know. There are a few faces that are not regulars here, so just a quick little spiel. This is the Tools and Technology Seminar Series. It is a weekly seminar series, discuss tools, technologies, methodologies, recently developed, currently in development, or just ones that maybe someone else developed but are of use to researchers, and we just want to let people know about. So there's a sign-in sheet going around. Please do sign. That just helps us justify the pizza. We want to be able to continue offering pizza each semester, so that's really helpful for us. So with that, I'll introduce our speaker, Chris Gates, who is the lead bioinformatics software developer for the Bioinformatics core.
Thank you, Marcy. So, as Marcy pointed out, sorry, can everybody hear me at this volume? Can people see me? Sometimes, if I get into the projector, let me know. I hate it when that happens. So we're going to talk about Conda, Snakemake, and Jupyter, and how we can use those tools to do more reproducible research. Before we get down into the weeds, I wanted to take a minute and say that we're going to take just a few seconds, and I want to learn a little bit about you, because it's going to help me shape and emphasize the pieces of this, if I understand whom I'm talking with. Then we'll talk a little bit about reproducibility in theory, and then we'll look at how those tools enable some reproducibility in research. So a series of questions, okay? And this is the kind of questions where you raise your hand to answer this. How many people, show of hands, use the command line on a semi-regular basis? Wow, a lot of people. That's great. Okay. How many people here are actively using one of Conda, Snakemake, or Jupyter? Okay. I'm just curious. Jupyter, Conda, Snakemake? Okay, that's good, good, okay. You're the expert. You just started, that's okay. So how many people here think they could name and describe more than 3 types of RNA? Okay, okay, that's good. How many people think they could contrast a Bonferroni correction with a Benjamin-Hochberg adjustment?
Gesundheit.
Yes. Okay, good. I may not call on you today, but it's good to know who those people are. How many people know what the dry principle is? Okay, good. So the reason I'm doing this is that bioinformatics, as we know, is a team sport, and everybody comes to it from a different direction. The hope is that we all land in the middle. I am coming from a software engineering computer science background. That's where my bias or my worldview is. And at the University of Michigan Bioinformatics core, the core itself supports researchers inside and outside of the university. We've done, I joined the core in 2013, and since that time we've done about 800 projects with researchers. Those projects can be very custom, they can be very standard, they can involve straightforward bioinformatic analysis, custom bioinformatic analysis, and sometimes even software development. And I play a role in some of those things at various times. I also help the core maintain its compute and storage environments so that it can do that analysis. So before we get into reproducibility, let me just pose this question, show of hands. Is reproducibility good? Show of hands. Most people are raising their hands right now. That's you're in the right place. So let me ask, why? Could anybody give me a reason why reproducibility is good?
Gives you better confidence that it's right.
Okay, it gives you better confidence that it's right. Agreed. Are there other reasons that reproducibility is good?
I feel it kind of links together with the dry principle, right? If somebody's already or if they've already created the wheel, and this is what they're saying, this is how the wheel's designed, you can go on to make the car without having to recreate the wheel. So as long as you can reproduce what they've done, then you can build off of it.
That's a powerful idea. That reproducibility is actually a form of encapsulation. It's a way of chunking knowledge up so that you can operate on a more abstract level. That's cool. I didn't think of that, but I like it. Actually, I did think of it, but I didn't think of it in the next slide. Any other reasons why reproducibility is good?
So other people can check your work.
So other people, so other people can check your work. These are good. You guys are good. So what I came up with is evidence of correctness, which was, I think, basically what you were talking about. In addition to enabling others to check your work, it really enables others to understand and extend your research. It enables the reuse of the research. But I think on a more profound level, for a couple thousand years now, we've made a distinction between what I think is true and what we accept as scientific truth. And the idea of reproducibility is embedded in the idea of what actually constitutes scientific truth. So reproducibility is actually really, really important. I think that it's very, very important. And it is also good. So how many people now think that reproducibility is good? Did I get anybody? Did I pick up anybody? How many people now, show of hands, think that we are good at reproducibility? Let's say the scientific community as of 2018. Are we good at reproducibility? Maybe you didn't hear the question. I'll ask once more to see if I answer it. Okay, just for the record, nobody actually raised their hands. Let me break that question down a little bit. How many people think how many people think that we're doing okay, but we could be doing better? How many people think that we're in some kind of a crisis of reproducibility? Okay, a lot of people. Well, I'm sorry that you feel that way. Unfortunately, you're not alone in feeling that way. In fact, in a Nature study executed, it was actually a survey in 2016, they asked 1,500 researchers, is there a reproducibility crisis? Over half said yes, there's a significant crisis. But 38% of them said yes, there's a slight crisis. How many times do you use that phrase? I want to use that phrase with HITS all the time. There's a slight crisis on the server. And actually only about 3% decided that we were doing okay. Now that's alarming, but it is just a study, or it is just a survey for researchers. But then when you get into more robust studies, psychologists created a consortium of 200 researchers, and they looked at 100 papers that were published in top-tier journals over the last 7 years. And they tried to replicate those results. And what they found was that across those 100 studies, they could only replicate 39. And those 39 were at a much smaller effect size. Okay, so 39% is not very good, but as we get closer to home, it's starting to look better, because in pharmacology, the number of drugs that fail when they proceed from phase 1 to phase 2 is 18%. Sorry, that's the number of drugs that survive, my mistake. So 82% of what you start with are going to fail out the first time you actually try to recreate it.
That's not the same as reproducibility. Reproducibility when they fail phases.
We will talk about those distinctions in just a second. Thank you for making that. Cancer in 2012, Begley and Ellis tried to replicate 53 cancer studies. They were able to replicate 6 of them. So, so it's okay. It's going to be okay. It's important. We think that we are not good at it. We are probably right. Can we do better? To answer that question, I think we do have to get into a little bit more detail about how we think about what is reproducible. So what we mean when we say reproducible, Victoria Stodden, does anybody know who Victoria Stodden is? Yeah, good. She actually spoke here several years ago, and her whole focus of her research is on reproducibility. And she offers up this framework, which I think is a useful framework. It's not the only framework. And in fact, different domains define the word reproducible and replicable in opposite ways. But for today, for this talk, I'm going to define them here, and we'll just have to use those words. So empirical reproducibility is the idea that you are studying a reproducible phenomenon and you are observing it in a reproducible way. I work in a dry lab. I work with computers. By the time things get to me, they've been through a lot of wet lab protocols. And in general, I trust that what they're doing right. And in general, that's a good assumption for me. If you are evolving new methods on your own, you have to consider, is what I'm doing actually a repeatable thing? Statistical reproducibility has to do with how you choose to analyze the data. And it is easier to understand statistical reproducibility by looking at its converse. And the converse of statistical reproducibility, what's the best example of having bad statistical reproducibility? What's the best example? Does anybody know? A phrase that's very often bandied about is p-value hacking, right? And p-value hacking is a specific example of an anti-pattern where you have an idea, a research question, and you think you know what the result is. And so then you modulate your analyses until you get the result you thought of. It's very simple. It's actually quite fun. And it's easy to produce results. And in fact, I'm not going to do it right now, but if we have time at the end, there's a website by 538 that lets you p-value hack, and it's super fun. But it's also really bad because, of course, that's not how science is supposed to work. You're not supposed to jack the analysis plan until you get the results you want or until you get the p-value that allows you to publish. That doesn't work. That's not reproducible. So the final idea about reproducibility has to do with computational reproducibility. And when I first heard computational reproducibility, I thought, oh, that must be kind of a new thing. I mean, given all this, big data. But the best explanation that I found for computational reproducibility is this quote. An article about computational results is advertising, not scholarship. The actual scholarship is the full software environment, the code, and the data that produce the result. That's a timely message. That was written in 1992. So they were struggling with computational reproducibility even then. And I can tell you in 1992, people were still publishing source code that you had to type in. Okay, so that's a problem. Now, if we take this as our definition of computational reproducibility, the ability to share and replicate the full software environment, code, and data, that's what we have to do. We have actually pretty good mechanisms for sharing data. We have reasonably good mechanisms for sharing code. The ability to share the software environment, we actually have good mechanisms now, but they're a little bit more recent to the game. This is actually where Conda helps, and this is where we start to get down into the weeds. Conda is a way of managing and sharing compute environments with other researchers. So before we dive deep down into Conda, I should mention that I am a Conda enthusiast. I am not a Conda expert. Okay, so if you have questions about Conda, I would love to hear them. But I will tell you about our experience with Conda at the core. So Conda improves reproducibility because it enables you to manage and share your compute environment with other researchers. Conda itself is a package and environment management system. Well, what does that mean? Well, if you cast your mind back to 1992, when that previous quote was mentioned, the easiest way you could actually share your compute environment was if you actually gave somebody your computer, right? And you could do that. That would be a simple, easy way to solve this problem. Is just put a line in the publication in your paper to say a completely fully installed laptop will be provided upon request. It doesn't scale well. It's the only problem. But the idea is perfect. You just want to mail somebody a little computer that has all the data and it has all the software and it's already installed. That's what you want to do. And that's basically what Conda lets you do. Conda it is connected with these repositories that understand the relationships of software and their dependencies. And it enables you to create, configure, and share the environments, which are like the little laptops inside of your computer. So let's look at how this works. Conda, in theory, is a very simple thing. There's only a few commands to manage this. So the first command that you typically execute when you're creating an environment is the conda create command, and all the conda commands start with conda. So you issue the create command and you give it a name. What it does is it says, okay, well, I'm going to reserve a small location somewhere, typically inside your home directory, and that's going to be where this little laptop lives. I'm going to stop saying the words little laptop and start substituting that with your compute environment, okay? So that's where your compute environment lives. It lives inside of this directory, which is inside of your home directory. And it tells you, if you want to use that little laptop, if you want to use that environment, then you have to type this other thing. You have to source activate that environment. Now, the next thing I type is source activate, and the only change is that my command prompt now has been prefixed with the name of that environment. So now I'm in that little laptop. Okay, everything is great. The only problem is there's nothing there, okay? So to make it a useful environment, I actually have to start installing software. How many people use pip? Pip. Okay. This is a little bit like pip. So I say conda install Jupyter, because I've heard that Jupyter is kind of a cool thing. I don't know what it's about. But I install it, and the first thing it does is it says, okay, I'm going to try to figure out if you want to end up with Jupyter, then what do I have already installed, and what do I need to get in terms of dependencies to make Jupyter work in this new environment? So it creates a plan, and it tells you what it's going to do. Then it tells you what it's going to download, and it turns out it's going to have to download like 82 megabytes of stuff to do this. And then it tells you, here are all the packages that I'm going to have to go get and install to make the Jupyter thing that you asked for work. And then it downloads them, it extracts them, it installs them. And then finally, at the end, it ends with executing transaction done, which is its fancy way of saying, I think it works. Then you could ask, well, if I were to type Jupyter, which Jupyter would actually be executed? And it would say, well, it's the Jupyter that lives inside of that environment. The environment. Stop saying it. So that's installing a package that Conda knows about. It turns out that Conda, to figure out how to install it, it has to communicate with something called a repository. And the repository has the recipe of how to install that different software. In this case, instead of installing it, I'm just asking it, hey, could you tell me more about the Snakemake tool? Because I've heard that's kind of cool too. In this case, it's giving me some more complex feedback. It's saying, well, I couldn't actually find that package when I looked in my channels. And the channels are like the channels, it's so funny, look at me. Like the channels on your TV. Sorry, I left everybody behind. They're like the channels on your TV. They are the places, the repositories that it knows about. And it says, I looked in the channels that I know about. I couldn't find anything called Snakemake. But if you really think it's out there, you should go to this website and then try to see if you can find it there. anaconda.org. So I go to that website and I type in Snakemake and I hit search and it comes back. Sure enough, yes, I do know about something called Snakemake. The version I have is 4.8.0 and it's in the Conda channel. Okay, so this is just another repository that has a different set of recipes to install a different kind of software. Conda is a repository that's dedicated to bioinformatics tools. So now I can say, well, now if I said Conda search, but look in the Conda channel for Snakemake 4.8.0, then it'll show me, well, I know about two versions, and one of them is optimized for Python 3.5, and another one's optimized for Python 3.6. That's great. And then I can say Conda install, and I can give it any number of channels, give it what I want to install, and then it goes through a ton of feedback trying to assemble all of the dependencies and link everything up, after which it finally says, yes, I think it works. And I ask, which Snakemake did you just install? Or rather, where is the Snakemake? And it's in my little environment. Obviously, at a certain point, it's handy to know what have I installed? What can I run? What are the versions of these packages? And for this, you just say conda list, and it lists all of the packages and the metadata about what versions they are and where they came from. It's also really nice every once in a while, you say to yourself, everything worked fine until I installed that one thing, and now nothing works right. Well, Conda actually keeps a list of revisions, so you can actually say, if you say list revisions, then this will say, well, this is revision 0, that's when you first created the environment, and revision 1 is when you installed Jupyter, and revision 2 is when you installed Snakemake, and within each of these revisions, it lists all of the packages that it either added or it modified. And you could at any point say, ugh, I've screwed it up utterly. I just want to go back to revision 1. And that's very easy to do. You say revert to revision 1. And you can go on from there. We created a little environment for this tools and tech, which I am calling reproducibility tools and tech. And but it's common to create many environments. There's 7 environments listed here, and you can see that with that command above, conda info ends. In the 7 environments, like I create different environments for different reasons. One of the reasons is that if I'm doing an analysis and I want to encapsulate all the software that I'm doing for the analysis, I'll create an environment. And then I install all the software that I need for that analysis into the environment. And then I can always reconstitute it, or I can always share it. And it's insulated from all the other environments. Another reason that I do it, you can see down here a little bit lower, I have a pointer, don't I? If I have to test software against different versions, which I sometimes have to do, I can create a build that has Python 3.6 with different versions of PySam. And so I can create an independent library. And that, again, is insulating all of these dependencies and making it much easier to manage. But of course, the point of this is to be able to actually share these environments. It's nice up to this point. It is very nice, and it would be worthwhile if that was where it stopped. But ultimately, I do want to be able to reproduce my research. So with a few simple commands, I can export this environment. And that exports basically a text file that describes how to reconstitute this environment. But then I take that text file, which in this case is called environment.yaml, and I email it to somebody, or I put it on GitHub or whatever. And they download it. And then they say, Conda environment create. And now they've got my compute environment. That's really nice. That's really nice. It is hard to reproduce other people's compute environments if you don't have some kind of a solution. And if it's hard, it really, I can tell you, materially interferes with your use and understanding of their research. Conda can be, I'm going to say, nuanced. 80% of the time it's wonderful and it does exactly what you want it to do. 20% of the time it's doing something that's probably very defensible and makes sense, but it's not obvious what it's doing. For example, I try to install Snakemake and I don't include all the channels. It doesn't always install the version that I expect. And there's always reasons, but you just have to pay attention. And in fairness to Conda, package management is a really hard problem. It's a hard problem. Ask somebody who installs packages a lot. Actually, don't ask them. They're very angry people. But it is hard. And so Conda is doing a hard thing, and I think it's doing it reasonably well. The other problem is that you lose the excuse. If you start using this intensively, you don't want to ask other people to install your packages. You start installing all your own packages. And then the problem is that you can't blame anybody else for all your problems. You become the problem. You're like, oh, I got to fix this, and I got to fix this repository, and I got to do a pull request because this recipe is wrong. But having said all that, Conda really does enable you to manage and share your compute environment. I think it does a great job. It is not the only game in town. There's a lot of good solutions for sharing your compute environment. There are heavyweight solutions that share an entire virtual machine. There are lighter weight solutions that share a container. There are software solutions. There are language and OS specific solutions. And what do you know? You can actually use those in combination. And in fact, I think, well, there's some colleagues at the Epigenomic Core that have made really good use of Conda and PackRep together. And I should mention that we were looking at Python software to install, but Conda was actually invented because there were things outside of Python that they needed to be able to install more gracefully. So Conda works with Python and R and Ruby and a bunch of other language environments. All that said, it is a little bit biased towards Python. So if you are using a lot of Python, Conda will help you. If you're using a lot of R, Conda will probably help you, but you got to watch it. So okay, that's Conda. Let's talk about Snakemake. Oh, sorry, I should have mentioned. If you have a question, the right time to ask the question is right when it occurs to you. I may not answer it right then, as I've already demonstrated with Jeff. But yeah, ask it when you have the question, because we're covering a lot of material and we're covering it fast.
Do you have an example of using the YAML file to recreate the environment?
This is an example of using the YAML file to actually recreate the environment. Yep. So there you go. And these little ellipses,
Stuff in between.
a lot of stuff. Like Conda is super chatty. But Okay, yeah.
Chris?
Yes. Alex.
So if I write, my own tools, for example, that aren't already in a repository, and I want to make those available to other people so they can reproduce what I've done, how hard is it to create my own repo?
It's not hard, and in fact, you probably wouldn't create your own repo. You could do it, and it's very easy to create a repo locally, and that's something that you can do if you're building a lot of weird pipelines. But if you build a tool and you want to share it, the move that I would probably recommend is that you actually upload it to Conda. And that's very easy to do mechanically. And the truth of the matter is, we had a tool that we built, and somebody came in from a person outside of the U said, "Ooh, I really want this in Conda. Is it okay if I put this in Conda?" And we're like, "Yeah, sure, put it in Conda. You can knock yourself out." And it's just a really simple recipe that you add to Conda, and then you issue a pull request to the Conda people so that they know you're actually doing a Conda thing. Yes.
Does it allow to install package directly from GitHub? Let's say the latest version is on the channel, but there are some updates that are not published in the channel yet, and just want to do kind of like pip allows you to do Git protocol and link to specific commit.
Right. So the question is, like, can you go outside of Conda to install like the way you would install with pip? Yeah. The answer is yes, you can. Conda, and in fact, if you do it with pip, Conda is close enough to pip, they're close enough in their relations, that when you capture the environment, it'll actually capture the other things that are installed in that environment via pip. So that's a good thing. The further you get away from the Conda install, it will allow you to install it in that environment. You have to be careful whether it's capturing that when you export the environment. Yeah. Cool, okay. So I mentioned, when I talked about what I do with the core, or I might have mentioned, but I'll reiterate. So part of what we're trying to do with the core is we're trying to identify and analyze patterns in DNA and RNA. And typically the way we do that is that we chain together a series of bioinformatic tools so that we can transform raw genomic data into some meaningful biological information. Now, oftentimes when we do that, we automate that as a scientific data workflow. And over the last few years, we've been using Snakemake more and more because Snakemake is a framework that makes it easier to build and execute good data workflows. Before I dive right into the belly of the beast, I want to consider a traditional data workflow. And I could dazzle you with bioinformatic transforms, but I'm not going to do that today. Are we in exam period right now?
Yes.
Okay. I'm not gonna tax those resources. We're going to keep it simple. All we're going to do is we're going to transform this raw chicken into fried chicken. And we're going to do it very simply. We're not going to use Snakemake. We're going to use a bash file. The bash file called friedchicken.sh. And there's 3 steps. You got to marinate the chicken with the buttermilk, then you got to bread that, then you got to fry that. This is a very simple workflow. It accepts 1 input, which is raw chicken, and emits 1 output, which is fried chicken. Okay? Got that memorized. Good. So, how would Snakemake approach this? Snakemake, instead of a bash script, it uses something called a snake file, which is a text file that defines the workflow. Now, it defines that with a simple markup language that defines rules, where each rule describes how to create an output file from an input file. Now, so far, this looks like a wordy version of our bash file, but we're not done, because in addition to the things that transform inputs to outputs, it also, for each rule, you have to declare all of the inputs and all of the output files. In this way, the snake file defines the dependencies for all of the input files and all of the output files across the entire workflow. That's what the snake file does. And that pattern of being able to articulate the inputs and outputs for each rule is a powerful pattern. With that under our belts, we can talk about Snakemake. Snakemake is a program that interprets the snake file against the file system and then runs rules as necessary to create your new output files. That's all it does. On the right, when you invoke Snakemake, Snakemake again reads your snake file and it says, oh, you want fried chicken? Okay. Well, to get fried chicken, I have to execute the fry rule, but before that I have to execute the bread rule, and before that I have to execute the marinate rule. Importantly, when you execute Snakemake, you never say, well, I want you to do this first, and then I want you to do this second, and then if that works, I want you to do this third. You never tell it what to do. You tell it what you want, and it figures out what to do. That declarative pattern is very, very powerful. and it has some very, very nice consequences. The first consequence is that it makes it very easy to extend Snakemake to new inputs. So if you want fried chicken, that's great, but maybe you're a little health conscious, you want some fried fish. Maybe that's not a big improvement. Yes?
How is that?
How is this different from a Makefile? I promise you I will answer that if you ask it again, but not yet. Before we leave Snakemake, I will tell you. So you can extend this with new inputs. So now I can get a lemon herb fried fish. And I don't have to change the snake file drastically. I just have to introduce a couple of wildcards. The data flow is very, very similar. It's not a big deal. Another nice consequence is that Snakemake is durable. And by durable, I mean that it crashes well. Now, Snakemake, I've never gotten Snakemake to crash, and I've tried. But I run bioinformatic tools. And the funny thing about bioinformatic tools is they crash a lot. Right? The inputs are weird, or the compute environment's not optimal. And it crashes, and that's just the way of the world. But when Snakemake crashes, it knows what the output is supposed to be, and it dutifully says, well, I didn't finish this, so I'm gonna remove it. It cleans up after itself, so there's not all these weird half-baked files lying around. So either a rule ran and it succeeded, or it was as if it never ran at all. That's really nice, because then when you have to restart a crash job after you fix the problem, you just issue Snakemake command again, and Snakemake says, oh, well, I don't have to recreate this because it's already there. And it starts exactly where it left off. That's really, really nice. In fact, Snakemake is so intelligent about this, you can ask at any point, what do you have left to do? And it'll tell you, this diagram was actually generated in Snakemake, saying, please show me with a visualization what's left. Snakemake is computationally efficient. If we think about...
Make it not remove things, because sometimes there's clues.
Yes, but you have to think about what you want in advance. And there's ways to do that. Absolutely. There's clues, exactly, right? If you want to do some forensic analysis of what went wrong, absolutely, yeah, absolutely. Snakemake is computationally efficient. If you think about a traditional bash file, and let's imagine that it takes a series of inputs we'll call input A, and that there's 4 tasks. And each of those tasks has an execution time, which is its height. And each of those tasks has a resource footprint, which is its width. So the full run for this entire workflow is the sum of the heights. But the resources I have to commit for that run, I have to do the max of the width. Now in the diagram, that makes white space. In your life, that makes waste. That's wasted time, that's wasted compute resources. And this problem gets worse if you think that you're going to have to run this on more than one input. Now maybe you could parallelize this by running all those things at the same time, but you've still got all that waste. Snakemake knows what's input, and it knows what's output. And so it's very easy to parallelize the Snakemake runs. So it's going to finish faster because it's running in parallel. And better than that, it knows what the resource constraints are in the individual tasks, so you don't have a lot of waste. So it finishes faster, it's less committed compute resources, which could mean less money. Snakemake is portable. This is how I run it on the workstation. Want to see how I run it on Flux? Like that. Want to see how I run it on Slurm? Like that. Want to see how I run it in Kubernetes orchestration? Like that. Want to see how I run it in Windows? Mac OS, it's compliant with Docker and Singularity, and it's compliant with Conda. So this is really nice. It's nice to build something that you can actually share. So another nice thing about Snakemake is that I can focus on the data. Now in a traditional workflow, of course, when you think about a workflow, you're thinking about the data. But you also have to think, well, how am I going to abstract out the parameters so that I can run it with different inputs? How am I going to build in the intelligence so that it doesn't rerun things that it doesn't need to? And how am I going to make sure that it works correctly on the different compute environments? And how am I going to articulate the different requirements for each of the tasks? And yes, I could build all this in. But then I'd be building a workflow management system. I wouldn't be building a data flow. I would rather just focus on the data and then attend to all these other concerns if and as necessary. And Snakemake lets me do that. So these examples looked at super trivial data flows, but Snakemake is not constrained to super trivial workflows. And these examples focused on a shell transform, but you can also just drop in Python right in that slot, or even R right in that slot. You asked the question, why is this different than Make? Right? How many people use Make? Because so different people use it. That's one. 2, it's got much more intuitive wildcarding than Make. So if you have to parameterize the inputs, it's much easier to do that. 3, it's easy to declare multiple outputs in Snakemake, which is hard to do in Make. And 4, Make doesn't have any provisions for submitting jobs to clusters. So the parallelization and the portability is a lot better. But it's inspired by Make. I mean, it's Snakemake. So, you got to speak up.
What do you mean by it's easier to make multiple outputs? Make is supposed to make multiple outputs.
For each rule, I can declare multiple outputs, which is harder to do in Make than it is in Snakemake. Yeah. But there's nothing wrong with Make. If Make's doing your job, do it. Makes a good tool. Yes?
Can you comment on this thing called CWL, Tunnel Workflow Language?
I cannot comment on CWL. Is anybody else using CWL? Yeah. I'll tell you this, Snakemake is not the only workflow management system. Like, there's a lot. And I think there's a lot of really good ones. I like Snakemake because it kind of fits our needs. But, yeah.
Invented by a version of some sort. And it's now running in the 7 bridges, like entire.
All right, yeah.
It's not in Galaxy.
Right.
That's why I know.
Yeah. Galaxy is a good. How many people use Galaxy? No, wow, okay, all right. Not a Galaxy campus, I guess. Galaxy is a good tool if you see it. Okay. Yeah. Okay. Let's see. Okay. Snakemake. Let's talk about Jupyter. How many people use Jupyter again? Show of hands. That side of the room. What's that about? Don't sit over here. How many people know what literate programming is? Oh, everybody just raise your hand that said Jupyter. You should raise your hand again. Who uses Jupyter? You know what literate programming is. So literate programming is an idea that was, this phrase was coined by Donald Knuth in 1984. And he wrote a book about it, but it boils down to, instead of imagining that our main task is to just instruct a computer what to do, let's concentrate rather on explaining to human beings what we want the computer to do. This was the idea that, like, anybody can make a computer do what you want. It's harder to make a person understand that. You should be writing programs for humans, not computers. And the kernel of his idea was that if we could combine not just the code, but also the narrative that explained the code and the data and the quantitative results and the visualization into the same artifact, into the same thing that we would share, then all of these things would become easier to use and easier to understand. This is great. This is a great idea and a super important idea. And Mathematica and MATLAB picked this up and they said, we're going to do it. We're going to do it with a notebook. Cool, scientific notebook. How many people use MATLAB? Oh man, all right. No shame in it. There's no shame in it. Yeah. And they picked that up. R looked at this and said, oh, okay, all right, we're not going to do a notebook, but we are going to support this idea, and we're going to do it through Sweave, and then we're going to do it through R Markdown. And Jupyter came along between 2001 and 2010, so it's kind of the new kid on the block in terms of literate programming and the notebook idiom, but it's got the benefit of hindsight. So, oh man, I so want to show this to you, but I'm so afraid to change my screen. How do you think
Be
so?
brave.
Yes, okay. I might not get it back, though, is the problem. All right.
Something every day that scares you.
Well, I already did that. All right, let's see what happens. I think I'm going to have to do this for a minute. Okay. It's going to work. Sorry. All right, so I am going to look this way. Okay. So I'm just going to launch a notebook. Oops, going to launch a notebook. Does that matter?
Maybe.
Okay. It's harder to type this way, I'll tell you that. Okay. All right, so the first thing you see is this big awful screen that actually is just a listing of the files that are in the directory. And I'm going to skip over this. It's not that exciting once you get used to it. And I'm going to start a notebook. Okay. I am in Jupyter Notebook. Fantastic. And in Jupyter Notebook, the way this is configured, I can execute arbitrary Python commands, arbitrary Python statements. So let me know if I have a typo. So I'm just going to assign an array to the value x, and then I'm going to execute that. Voila. Amazing. I could look at what x is. That would be cheating, but I can do it. And I'll just do one more fancy one, and then we'll take a look. We'll talk about what's actually happening here. Okay. So in the notebook, you have this concept of cells, and the cells have an input. All cells have inputs, and some cells have inputs and outputs. In this cell, there's no output because there wasn't really anything returned from the command. This one, I'm saying, well, I just want to know what x is, so it's going to print the output. And the cells can have more than one line, and in this case, I don't even know, what is that, Jeff? I don't know. What is this? Comprehension?
This is comprehension.
Okay. So I do a comprehension that assigns a new variable and then yields it out. So this couplet, this kind of call and response of, I do this, you show me that. This is a very familiar pattern, right? Because this is the command line. This is what the command line does. Amazing, we've invented a command line. But it's not just the command line. An important idea is that I can come up here and I can say, well, the truth of the matter is, I kind of know what x is. I don't need to see it because I just assigned it. So I'll tell you what, I'm just going to combine these. I have just rewritten history. That's harder to do in a command line. And the important thing is, in a command line, the best thing you can do is share your history, the history of your commands. But with this, I can share this document, this thing, this Jupyter notebook, and they have all of my inputs, and they have all of my outputs. And I can arrange this so that it makes the most sense. I don't know why I got up there. I'm going to show you an extended example of this. I'm going to come back to, dare I, it's over here, isn't it? This is only a slightly more complex version of what we just saw. But here, I do a little bit of that. And this is an interesting cell because this cell is not a Python cell. This is a Markdown cell. Using a Markdown cell, I can use very, very primitive Markdown language to introduce some simple formatting that enables me to create that narrative that explains what you're looking at or why it's important. How many people use LaTeX? How many people use LaTeX? All right. You can use LaTeX here if you want, and it interprets it perfectly. And unlike a typical command line, I can embed graphics and visualizations in here. And this is again kind of a toy example, but let me give you a slightly more robust example. This was a homework assignment that I did a couple of years ago. This is a clustering example. But the point is that this combination of code and results and visualizations, they really make a more useful shareable artifact. This is what I submitted as my homework. Well, I mean, I've turned it into a PDF, which is very easy to do. So that idea that you're working with a more, sorry, how do I get that? Can I do this? Dare I do this? Oh, hey, that worked. So I'm sharing a more valuable artifact that combines, it's like painting in color after you've been using black and white. Another important aspect of how Jupyter does this is that it partitions the beauty or the user interface with the brains, which it calls the kernel. So on one side, like when you're interacting with it, you're interacting in a web browser, and you're typing things up in the cell down here, and then those things are read by the kernel, executed by the kernel, and the results are printed by the kernel, which are sent back out, and it just loops. That's why it feels like a command line. That's exactly what command lines do all the time. They just do this loop. But because this is split conceptually between the brains and the beauty, it enables me to make some interesting choices. I can run Jupyter all on my workstation and then attach to a server that has data that's far away. But maybe that doesn't make sense. Maybe if the data processing is really intensive, maybe it makes sense for me to run the kernel right next to the data. and then just have this web app. Very thin client, very efficient. The other thing that's really nice about this is that the notebook interface is really well defined, and the messaging protocol is really well defined. And as soon as they did those definitions, people realized this is not just a Python thing. This is you can do anything that supports a command line with this. So this is the R kernel, and this is an R notebook. The R notebook has that same in-out field, but instead of Python, it's all R. Running against an R kernel, just the way you do in RStudio, if that's the way you wanted to do it. And in fact, it supports like 100 kernels. Jupyter, the word Jupyter is for Julia, Python, and R. Those were the first 3 kernels that they built, Jupyter. Jupyter Lab is out there. How many people use Jupyter Lab? All right. Jupyter Lab is the future of Jupyter. It may not be the present of Jupyter. Jupyter is sweet. I love Jupyter. Jupyter Lab is, in terms of the look and feel, it's a little bit improved. I don't know that I like it that much more. But importantly, there was a problem with the architecture when they conceived of Jupyter that prevented people from building really portable widgets. And they fixed that with Jupyter Lab. So Jupyter Lab, and Jupyter Lab has a zillion committers. So if you haven't switched to Jupyter Lab, you might consider switching. If you haven't started Jupyter at all, you should start with Jupyter Lab. If you're really deep into Jupyter and you use some really esoteric JavaScript, stick with the notebook. And incidentally, the notebook format hasn't changed when it went to Jupyter Lab, so they work exactly the same in Jupyter and Jupyter Lab. The Jupyter ecosystem is a little confusing because there's a lot of words, but it started off as IPython, and then it became Jupyter, and now it's Jupyter Lab. Be aware that Jupyter Lab is very fresh. There's a thing called Jupyter Hub, which makes it easy to create a multi-user Jupyter notebook so that zillions of people can use Jupyter all at once. That's something you'd use for like a class or even an institution. Jupyter notebooks render pretty well on Git. They don't render perfectly all the time, especially if you're using a lot of weird interactive JavaScript. But if you just go to a Git page and you look at a Jupyter notebook, it's going to look right. There's also a thing called Binder that enables you to create a Jupyter notebook and then publish it, and it captures all those dependencies in a container. So it's really easy to share. It's also really easy to see other people's notebooks. Jupyter is not a software IDE, and it's not a very powerful text editor, so I'm keeping Atom and I'm keeping Eclipse on my machine. But it is really nice for data analysis. Okay, last thoughts. You know, the problem is this is a lot of words. So I'll just say, these are tools. What we've talked about up to this point are tools. And tools can enable better behavior. Behavior is the key. We have to be better about sharing. The tools enable us to share in a reasonably safe, productive way. But this is what we have to do to make reproducible research. We have to share our compute environments. We have to share our code. We have to share our data. And it would be, and there are often reasons why we can't share things. And I understand that. I'm not saying you have to share everything, but it would be nice if the default position was, let's share this unless we can't, rather than, why should we share this? So, does anybody know what the Joel test is? Get out of here. I'll talk to you later. The Joel test was this test that this guy came up with to see whether or not he wanted to work for an organization, a software organization. He'd ask all these questions, yes or no questions, and then he'd figure out whether or not he wanted to work there. And somewhere along the line, somebody realized, well, that's kind of a snarky way to be. But these are interesting questions, and they provoke good discussion. I present to you these questions as a way to think about reproducibility and whether or not our actions are aligned with our espoused values in terms of reproducibility. I'm going to go through them all. Right. I think we've all established that reproducibility is good. And coming from a software background, I think of reproducibility as to research, as usability is to software. Yeah, it's harder. It requires more thought. You have to pay a little bit more up front, but you're going to give a better researcher experience. That's a weird phrase. You don't hear those words together. It's a better researcher experience, like a better user experience. You know what the thing about it is? When it's easier to use another person's research or understand another person's research, you get more use, you get more citations, and they will extend your research. This is a good thing. With apologies to Alfred North Whitehead, research advances by extending the number of important operations which we can perform without thinking about them. The tools that I've gone over today enable us to stop thinking about some of those mechanical operations so we can focus on more important, more profound questions about our research. A lot of interesting information. If this was boring, don't go here. If you liked it, you should go here. And I'll just call out Software Carpentry is a group. I'm a member of this group. I see a couple people. Scott, I see Zena, I saw Stephanie. You guys have a training coming up?
Monday, Tuesday.
Monday and Tuesday.
Yeah.
Goodness. If you're interested in software carpentry, if you're interested in using computers more effectively in your research, you should follow those two people, Zena and Scott. They're going to help you out. With that, I'd like to thank the Bioinformatics Core and also the Kretzler Lab for indulging me in these philosophies, which are wholly my own. And with that, I'll take questions. Thank you. Did I leave any questions behind?
Phase 1, phase 2.
Yeah, you're right. They're not different. They're not the same. I think no, I mean,
Phase 1 is first in humans, so all the experiments before are not perfectly predictive of what's going to happen when you put them in human.
Right, absolutely. I'll say, though, that I think what that is for me is emblematic of the importance of defining what you mean by reproducibility when you start having that conversation with anybody, because it is the literal truth that if you walk over and you talk to a computer scientist and you ask them what is a replicated study and what is a reproduced study, and then you cross over and you ask a biologist what is a replicated study and what is a reproduced study, they will give you exactly opposite answers. They're very precise, but they're exactly opposite. So yes, definitely define your terms. Yes,
quick
Jude.
comment that
Yes.
go. It's great. I learned a lot. Of course, NIH is encouraging the movement to from big data to the cloud. So they actually want to discourage study-specific or consortium-specific data coordinating centers. So one thing they are grappling with is when they define the digital objects on the cloud, even define the workflow, there is still a challenge of a lot of tasks have too many tools to choose from. So you can call this a collection and call this an app store or vending machine. But there's no community agreed standards on which is better to put into your workflow. So the idea that many people are thinking is to somehow develop a rating system so that the master workflow gets more people contributing to it or gets voted up and then made more efficient or more literate. So that it's a combination of a totally democratized but chaotic Twitter, but have some tiers of vetting to make it healthy. So that's my comment.
Yeah, and I'll mention that this is a reproducible tech stack. It is not the reproducible tech stack. This is obviously, there are alternatives to all these tools, and there's not a lot of convergence yet. So I would welcome convergence. It would frankly make my job easier if everybody was speaking the same language. Thank you.
Any other questions? Thanks.
Thanks.